Yeah, so the plan for the next little bit, so our next, I guess, session is going to be a round of lightning talks, which I actually need to get those pulled up, so if you give me just a few seconds. We're going to do lightning talks. These are going to be by our poster presenters. I think most of them are giving a lightning talk, maybe not all of them. And then immediately following this, we're going to move into the poster session. And again, you can access the poster session by going into GatherTown. So it's all right there in the same room. All you have to do is walk up, walk north, and you'll find the posters. The presenters should be standing next to them if you want to have a little chat with them. Otherwise, you're free to just walk in there, talk with some colleagues, look at posters. Oh yeah, someone asked to post the GatherTown link. If one of my co-chairs wouldn't mind doing that very quickly, put that in the chat so people can quickly access it. And then you're also welcome to play with the Miro board during this time. And then we'll have like kind of a 20-minute break kind of embedded at the end of the poster session. So we'll reconvene here in WebEx for the next set of oral sessions at, I believe, 2:40 Eastern time. So again, everyone take advantage of the poster session, go see the great posters, stretch your legs for a few minutes, and then we can reconvene at 2:40. Let me share. Ricky, could you make me a presenter real quick so I can show the slides for some of the lightning round presenters? All right, I will go into full screen. Are you all seeing this okay?
Yeah, looks good.
Thanks.
Okay, so I think I'm going to introduce the lightning speakers, but when you see your slide come up, get ready. You have a minute to talk. So our first speaker is Alexander Braun, talking about lunar lava tubes.
Okay, thank you. So this study, we had a number of objectives, but the main one was, what would it take to actually confirm a lunar lava tube on the moon? And so we did a number of modeling studies, considering what geophysical tools could apply to shed light on the existence of a lava tube. And we focused on an area which is the Marius Hills region on the moon, where we have one of these sinus rills, which are potential candidates for lava tubes, but nobody really knows. Where also we have found these openings, pit craters, such as seen here from identified by Haruyama in 2009. So our question was, is there an extent of this opening in a lateral direction? So for that, we developed a number of modeling tools, including gravity, so rover-based gravimetry, using a Vega instrument developed by Canadensis. We also proposed ground-penetrating radar and modeled a lava tube, how it would look like in a rover-based GPR system. And we had a big focus on survey design as well. So overall, we propose these geophysical rover-based techniques to de-risk many different targets, not only at this pit crater, in order to make sure first that something exists what we actually want to study. Thanks.
Thank you. Just about right on time. So the next speaker, I think, was Marshall Eubank.
Yeah, oh. I don't think I have a slide, so I just have a blank one up.
Oh,
but you're still welcome to do 1 minute.
Marshall Eubanks is next up to talk about his poster. So if you want to speak.
Oh, can you hear me?
Yes.
I put on the camera, but I don't actually see that. Okay, so this in some ways is very similar to what Thomas Waters talked about, if I have a little different wrinkle, if you would, on it. I've become very interested in active lunar tectonics. I mean, for a long time, everybody thought the moon was just dead, except for things that hit it or poked it. So in other words, except for tidal perturbations, which are tens of centimeters maybe globally, and except for meteorite impacts, nothing happened on the moon. And now we find that that's not really the case. There has excellent evidence for, in my opinion, for active lunar tectonics. And they seem to be connected to these wrinkle ridges, but also some other areas, and there's lots of them. And by lots, I think the way of thinking about that is, of the 5 or so surveyors that worked, and of the 5 or so Apollos that worked, 11 total missions, at least 2 of them landed within walking distance of what looks like an active tectonic area. Apollo 17 and Surveyor 6. These things are not that uncommon, and so that suggests that the CLPS, probably any CLPS landing, could almost find one of these nearby to investigate. And that suggests to me, how do we do this on the Earth? Well, there's a variety of ways, but geodesy is a crucial one. And so we've been working on geodetic ways of looking at this. In other words, actually looking at the ground motions that have to be associated with any major earthquake. And some of these are major earthquakes. They're bouncing boulders around.
Marshall?
It would be very bad for an astronaut who happened to be there at the time. Thank you.
Thanks. Thanks very much. Sounds really interesting. So yeah, please check out the poster. You guys get into Gathertown. And so I think the next lightning talk I signed up was Norbert. Oh no, I've got the wrong order. Did
No, I don't have a slide for Norbert
Oh,
either. Sorry,
for
that was
Norbert,
my fault. So if Norbert's on, I'll go
I'll
ahead
have
and
her do the
talk.
give a brief.
No, yeah, I thought I did submit a slide. So, but
I can see if I can find it real quick. I apologize. But if you want, go ahead and keep talking. If I can find it, I'll pull it up.
we did make new maps of CO2 cold traps based on diviner data. In particular, we included all the time dependence in this analysis, and the seasons turn out to be important. So I wouldn't get quite the right CO2 cold trap area if one wouldn't consider the seasonal variations in temperature. And so we ended up with a new map, and by far the largest CO2 cold trap is on the floor of Amundsen crater, right? I think a single patch is like a third of all the CO2 cold trap area. And CO2 is potentially interesting, because radiation can create, you start out with carbonaceous ices, and radiation will create more complex organic molecules. And it's obviously also interesting for ISRU purposes. Methalox, for example, is a rocket fuel which requires carbon. And so I have a post on this, and you also published a paper on this in GRL this month.
Right, thank you. Jill, are you talking? Because if so, you're muted.
I'm sorry. I
But-
thought I was unmuted. Good job at staying on exactly a minute, Norbert. So yeah, our next talk will be given by Vishnu. I'm going to try. Viswanathan?
Vishwanathan, yeah, I got it.
Perfect. So go ahead.
Okay. Our poster builds the case for why it's very desirable to have a lunar laser ranging retroreflector situated very close to the south pole of the moon. So surface retroreflectors are currently on the moon that have enabled like long-term geodetic monitoring capabilities, and they continue to be a priority for future lunar missions. What makes the South Pole special for laser ranging is that it will provide the largest north-south separation to help understand both latitudinal librations and subtle signatures on rotation from the lunar interior. Now, second, a large reflector will massively improve the signal return, but the thermal environment places a very strong limitation on its size, which can be bypassed if it's placed in a cold region, providing sufficient Earth visibility. That's what you see here. With the potential to also bring in more participating stations from global Earth stations. Now, carrying a LiDAR on board would further enhance the science capabilities, not only from it would help create a high-resolution spectral map of the PSRs, but enable monitoring of temporal variability of dust from surface operations of frost formation to the level of few tens of nanometer. So yeah, thanks for your attention, and feel free to join me for post number 6 for discussions. Thanks.
Great, thanks. So I didn't see our next in the program. I didn't see the next person on the list. So I think we're going to move on. And we'll circle back at the end if I miss people. So the next slide is from Stephen Dare, talking about Chromehound capabilities for CLPS deliveries.
Hello, mic check.
Yes, you sound great.
Awesome, thank you. Hello, my name is Stephen Dare. I'm a Master's of Systems Engineering student from Johns Hopkins. This project focused on lunar landing sites for astronauts as well as
Stephen?
a modular robotic system. Yes.
Sorry, your mic seems to have gotten very quiet.
Is this any better?
Sort of.
How about now? Any improvement?
You're kind of going in and out. However you started out.
It's very hard to
fine.
hear.
It's very hard to hear now.
Can I just take over for him? I'm his intern. All right, cool. So this is a lunar landing sites for astronauts in our Chromehound robotic rover. We selected Shackleton Crater and identified 6 sites where the altitude and temperature were safe for human habitation. One of our science objectives is to set up a lunar LIGO. It dates back to 1990, and it would be able to provide astrophysics data on gravitational waves as a second baseline station, as well as active tectonics on the moon and space weather sensing. And our modular rover will assist astronauts and develop infrastructure between human habitations. And the modular ability of Chromehound will allow for long-term habitation on the moon as well.
Great.
Thank you.
Thanks very much. All right, and so our next lightning round speaker is Cole Nypaver.
All right. Can everybody hear me?
Yeah, you sound great.
Awesome. Okay, thanks everybody. So in this work, we observe an abundance of meter scale boulders at the rims of these kilometer scale craters all across the lunar maria. And these craters are very old, so 2 to 3 billion years old in some cases. Now that observation is really only interesting because an abundance of prior work has shown that even the largest boulders on the lunar surface should be completely destroyed in 3 to 500 million years max, right? And we want to know more about this. We want to know if this is ubiquitous across the lunar surface. So to investigate this observation, we utilized 2 separate lunar reconnaissance orbiter data sets, remote sensing data sets, which are sensitive to surface rocks. And we measured the crater rims and ejecta for 6,240 craters in both of those data sets. Then we binned those measurements based on crater age, and we ended up with about 30 bins with 50 to 200 craters each. And you can see all of those bins in the results there up in the top right plot. And what this is showing us is actually that the crater rims, the rock populations of the crater rims, are elevated above the ejecta in both of those data sets for the majority of craters in our data set, irregardless of age. So again, I mentioned earlier that prior work has shown that surface boulders break down relatively quickly. So what we're actually thinking is going on here is that these boulders are being exhumed at these topographically high crater rims. So they're sort of popping out from the subsurface due to mass wasting and the downslope motion of the overlying regolith. Now, what does that have to do with landing site selection? Well,
Cole, about 20 more seconds.
Gotcha. Boulder exhumation at crater rims implies that these boulders are in situ, meaning they're not distal exotics and they're unlikely to have undergone transport from some other portion of the moon. Therefore, they're going to provide the best temporal and petrologic interpretations, whatever your science goals may be. So stop by my poster. We'll talk more about it. Thanks.
Wonderful. Thanks very much. So I think that's the end of my list.